Okay. Hello everyone. Today I'll start class. So today we will be talking about how to count with geometric figures such as counting how many squares, triangles, or like how many points of intersection in a plane between like a circle or a triangle. So we'll cover some basic knowledge and some formulas first, and then we will move on and also go over some uh problems. And before I begin talking about those, I'll introduce myself. My name is Aaron Kuang, and I am an eighth grader at Green Hill School. I have done a lot about math, have qualified for Amy last year, and more stuff about that. So let's get started. So our first like theorem or stuff is that the maximum number of intersections between any number of lines is always n2 or n.
太安静了。
Okay. Give me a second. Can you guys hear me better?
Yeah.
Okay. Um, let's see. Okay, so let's start over again. So our first like theory or rule is that the maximum number of intersections between n number of lines is n choose 2 or n times n minus 1. So the the reasoning, like the proof behind this is that if there are like so let me explain what it actually means. So like if we have like five lines or like three, if we have four lines right now, then like the maximum number of intersections is 4 times 4 minus 1, which is 3. All of this divided by 2, which is 6. So the number of maximum intersections between four lines is 6. And the reasoning behind that is to make one intersection, we need two lines. So if we take four lines and we pick any two of out of those four lines to make an intersection, that's how many intersections there are. So since we have four lines in our example and we take two of them, it's 4 times 4 minus 1, which is 3. So 4 times 3, and we divide all of that by 2, which is 6. So there are 6 intersections between any four any number of lines. So if we broaden that example and we say there are n lines, then it's n times n minus 1 divided by 2 intersections between those n lines. So here's our second rule is that the maximum number of triangles between n points is n minus 3, or if we want to expand it, it's n times n minus 1 times n minus 2. All of that divided by 3 times 2. Whoops. So, okay, so we have 4 points right here, right? And then to create a one triangle, we need 3 points to create one triangle, because we have 3 points, we could just connect the three lines between them and we form one triangle there. So then since we need 3 points to make one triangle, out of those four dots, we pick three of them. So we have four dots, and then we pick three of them, which is equal to, which after you calculate this, it's equal to 4. Because so then if we then like broaden our understanding of this, then we can say if there are n points, we pick any three of those n points that we have, and then after we pick any three of them, with those 3 points, we make one triangle. So then if we have so in our example we have 4, so we pick 3 dots and that makes one triangle. So if we have n, we pick n of the 3, which is which if we expand it, it's n times n minus 1 times n minus 2 divided by 3 times 2. So then that is the number of triangles made of n points, the maximum number of triangles that can be created. Now on to our third one. For a rectangle with m rows and n columns, the total number of rectangles that can be counted or created is m plus 1 times n plus 1 m plus 1 choose 2 times n plus 1 choose 2. So then the reasoning, so like the proof behind this. So we start off with an example again. If we have if we have three columns and two rows. So to make one rectangle, anyway, if we make a rectangle, we always need two horizontal lines and two vertical lines to create one rectangle. And that rectangle is this one right here. So we established that to create one rectangle, we need two horizontal lines and two vertical lines. So then in our example of a 2 by 3 rectangle, there are three horizontal lines here. 1, 2, and 3 horizontal lines there. So then and then we also have four vertical lines. We have one vertical line here, two vertical lines here, three vertical lines here, and the fourth one here. So then after we know that there are three horizontal lines and four vertical lines. So then out of the first three horizontal lines, we pick any two lines out of those three to create the two horizontal lines to make the rectangle here. And then after we pick those, we have three choose two ways to pick them. And then after we pick two horizontal lines out of those three horizontal lines we can pick out of, then we go on to the vertical lines, the two vertical lines we need, and then we have four choices here to choose from. And then after we choose those four vertical lines, then we choose two out of those four vertical lines, and then the two vertical lines we choose will be the two vertical lines here to make that rectangle. So then we have four choose two vertical lines, and then we could compute this value for the total number of rectangles that we could create out of this 2 by 3 grid. And then we like replace the 2 by 3 by m by n rectangle. So then for m rows, we will have m plus 1 horizontal lines out of those m rows. So then out of those m plus 1 horizontal lines, we will pick two of those horizontal lines to create the two horizontal lines needed for one rectangle here. And then after we pick those two horizontal lines we need, then we will pick out of the n columns, there are m plus 1 vertical lines. And then after we pick two of those from the vertical lines we need for the rectangle, we multiply those two values together, and then we get the total number of rectangles in an m by n grid. In our fourth theorem, the number of squares in an n by m rectangle is equal to m times n, plus m minus 1 times n minus 1 plus m minus 2 times n minus 2, all the way down to m minus 1 times 1. It is where m is greater than n. We keep that 1 in mind. So then the proof behind that is, so if we start off with an example of a 3 by 3 grid right here. So we count the number of ones we have, right? So the 1 by 1s rectangles we have have 3 here, so we have 9 of them right now. And then the number of 2 by 2 rectangles we have is just, so to count 2 by 2s, we really just count the center little thing here, like the center things. So we have 1 of them here, 2 of them here, 3 of them here, and a fourth one here. So we have 3 minus 1 of them times 3 minus 1, which is really just 2 times 2, which is 4 of them. So we have 4 2 by 2 rectangles. And then now we move on to 3 by 3 rectangles, 3 by 3 squares I meant. We only have one of them in this 3 by 3 grid, so we have one of them in this grid. So then we only have one of them. So then after we add them up, we have 14 of them in total. Give me a second. 14 in total. And then so this is, we counted by casework. So now let's plug it into the formula to see if it actually works. So if m is 3 and n is also 3, if we plug it into the formula, it starts off with a 9, and then we add on a 4 here, and then we add on a final 1 here, and then we add this total number up, and then we get 4, and then our sum of it is also 14. So then our formula works. So then that's why this is just a really useful like formula to keep in mind, because it allows you to compute them quicker than doing casework through every single square that is possible. So because like if we expand the grid to a 5 by 10 grid, it will be takes way too long to go through every single casework, when we could just plug it into this formula and quickly find the answer. So on to our fifth one. So the number of diagonals in a polygon with n sides is n, we choose 2 minus n, which is also the same as n times n minus 3 divided by 2. So the reason behind this, we can start off with any shape, which we'll start off with a pentagon in this case. So then the number of diagonals so to create one diagonal, so from this point we have right here, to create one diagonal, we have to connect it to a side that is not one of the adjacent vertexes. So if we follow along with this section here, right here, so we have n choices. So from our starting dot here, we have 5 total dots we could choose from, but then we have to minus 3 choices, because we cannot pick this one, nor can we pick the one that it was starting from, or the other adjacent vertex, because those adjacent vertexes, they're not diagonals anymore, they're really just adjacent side from there on. So then if we just connect it from here, and if we have 2 choices here, so it's 5 minus 3, we have 2 choices for each vertex we pick. So we started out with this one, and there are 2 choices for that one vertex. If we rotate this one over here, there's also going to be 2 choices here and from here and here. So for each vertex, there's always going to be n minus 3 choices. So then in this case of pentagon of 5 sides, we have 5 minus 3 and for each vertex, and then we have 5 vertexes. And then we have to divide all of this by 2, because if we start out with this one as our starting vertex instead of this one or this one, we cannot go to this one or this one. So then we only could go to this one and this one. But then notice here, both of these are counted. So in order to get rid of the overcounting that we have to experience right here, we have to divide everything by 2. So then everything is only counted once, so we don't overcount. So we could compute this value, which is equal to 5 for a total of 5 diagonals in this polygon of 5 sides. So then if we generalize it to n sides, the formula will be n times n minus 3 divided by 2. In our sixth formula, we talk about the maximum number of intersections of a diagonal in a convex n-gon is that much. So we have a pentagon again. We have 5 sides, and in order to okay, so we have here. Let me change this actually. So I think I wrote this wrong. Let me change it. So the maximum number of intersections of let's just change this completely. So the maximum number of intersections of n points in a plane is n choose 4 because, okay, let's start off with this idea. To create one line, we need 2 points. To create one line in between. And then to create 2 lines, we need 4 points right here. And then out of these 4 points, and then, so since we have 4 dots here, and then after we pick any 4 points, like 1, 2, 3, and 4, there's only one way to connect these points such that there will be an intersection point between those 4 points. And the intersection is right here, that one. So then, if we have like 10 points in one plane, we could always just choose 4 of those 10 points in that entire plane. And then of those 4 points, there's only one way to create an intersection point. So after we have those 10 points and we create that intersection point, then it's 10 choose 4 ways to find how many ways there are to get that for the number of intersection points. Before we move on to problems, are there any questions that anyone has? Okay. So if no one has any questions, then we could move on to the problems I have prepared for today. In our first problem, we talk about the maximum number of points of intersections of a circle and triangle. I'll give everyone 2 minutes to try this question, and if you're finished, you could send me the answer in the chat privately. Thirty more seconds. Okay, thank you for everyone that actually attempted the problem and gave me an answer. So now we will talk about the problem. So it mentions about one circle and a triangle here, and the maximum number of intersection points between the circle and the triangle. We have, there are many ways for it to intersect, but the most possible way is that if we intersect it like this, which gives us a total of 6 intersections here. 1, 2, 3, 4, 5, and 6. So if anyone, so our answer is A right here. Onto problem 2. One circle and 2 squares lie in a plane. What is the maximum number of intersections of 2 or more of these 3 figures? I will give you 2 minutes to solve this question, starting now. Maybe one more minute since I haven't gotten that many responses. Okay, so I'll start talking about the question now. Um, so in the question we mentioned about one circle and two squares right here. So we could split this question into case work. So we can start off with one case of how many intersections between a circle and one square. So the maximum number of intersections between a circle and and one square is 8 intersections. Here, here. So since the square has 8 intersections between a circle, we have two squares. So that means a total of 2 times 6, 2 times 8. So we have a total of 16 intersections between a circle and one square. So then if we have two squares intersecting each other, then we have a total of 8 intersections again, as we can see here in my diagram about that. So we have another 8 in the diagram again. So then our answer, so then 8 plus 16, so we add up the two cases of a square and a circle, or two squares. So if we add up the total number, our answer is 24 here. Any questions about that problem? Okay, no questions. We can move on. Okay, problem 3. I'll give you guys about three. I'll give you guys about 4 minutes to try this question. This question's a little more challenging than all the previous questions. So far, I have only received 2 responses. If I will give a quick hint about this question. So, if we have any two circles intersecting, the maximum number of intersections between any two circles is 2 intersections. So since we have 7 circles, how many? So if we have 7 circles, we choose 2 circles and then 1 more minute. Okay, I'll start actually explaining the question now since a good number of people got the question correct. Okay, so as my hint stated, the intersection between any two circles is 2 points. So if we have 7 circles, we choose 7 circles, we choose two of them that we pick, any two, and then of those 2 circles we pick, we will have 2 intersection points. So then if we, so then our that's our number of intersections of those 7 distinct circles. So after we compute this, our answer is indeed 42, which is our answer of D. And I hope no one actually went to draw this question out because it would be a really big pain. Uh, any questions about this question? Okay, no questions. Next question. Problem 4. Uh, 5 distinct points on line N, A, B, C, D, E, and 6 distinct points on line M, F, G, H, I, J, K are chosen to maximize the number of intersections in the shaded region among the 30 unique line segments connecting one of the 5 points one on N to one of the 6 points on M. Find the maximum number of intersections in the shaded region, excluding the intersection on the point of at points on line M or N. I noticed this question does not have a diagram. I'll quickly draw one. So, the yellow highlighter is the shaded region. All right, so I'll give everyone about 4 to 5 minutes to try this question. If anyone has any answers, send it in the chat to me privately. have only received one answer, and I will give everyone a small hint about this question. Remember our theorem about any four dots. There was only one way to any four dots. We can make two lines out of those four dots, and then out of those two lines, we have one intersection point there. So apply to here where we have five dots on one line and six dots on the other line, and then we pick four dots, two dots on one line and two dots on the other line. Okay, I'll start explaining this question. Okay. So, in this question, we mentioned about how we have five dots on one line and six dots on the other line. And then to create an intersection in this shaded or highlighted region, of those five dots on this line, we pick two of them, and then two of them. So we have five, choose two of them on that line. And then on the other line, we have six dots, and of those six dots, we choose two of them. And then after we choose, so example, if we choose F, and then we also choose I, and then we choose B and E, if we connect those four dots, there's only one intersection between those four lines, and it's right here of those four dots, and it's right there. So then, if we pick any of those five dots on line M, and then we pick two of them, then we'll have two of the 4 points needed for our theorem about any 4 points. And then on the second line M, we pick six of them. Then of those six we pick two. Then we have the other two needed. But if we cannot pick three dots on one line, because if we pick any three or more dots on one line, if we pick F, I, K, and D, we already have an intersection here. The intersection's at I, but then in the question it says excluding the intersections at points on line M or N. So those do not work. So we have to have two on line M and two on line M. After we compute this, our answer is 150. Any questions about this problem? Okay, moving on to the next question then. This is an actual AMC 10 question. It's a 2004 problem 16. The question reads, in the 5x5 grid shown contains a collection of squares with sizes from 1 by 1 to 5 by 5. How many of these squares contain the black center square? I will give everyone maybe 4 minutes to try this question. Okay, I'll give everyone maybe about 30 more seconds to try this question. All right, I'll start explaining this question. Um, so the question talks about how in a 5 by 5 grid we have a collection of squares with size 1 by 1 to 5 by 5. So we want to know how many squares contain the center square here that we want to achieve. This center square we want. So there are two ways to do this question. I'll explain one way first. So one of our ways is just casework. So we start out with casework, and we start out by counting how many squares include this center square. So 1 by 1 squares, we have only one way to pick, because that's just a black square. And then for a 2 by 2 square, we have some choices now. We have this, we have one of them here, and we have a second one here. We have a third one here, and we have a fourth one here. Oh, whoops. So then for our 2 by 2 squares, we have a total of 4 squares that we can achieve. Okay, so now we move on to 3 by 3 squares. So in a 3 by 3 square, we all 3 by 3 squares work in this situation that include the center square. Because all like in a 3 by 3, there's only so much space in a 5 by 5 square. So if we have a 3 by 3 square, it's gonna fit inside the square. So then, all 3 by 3 squares actually work in this situation. So then there is a total of let me give me a second. We have a total of 9 squares in this situation. And then all 4 by 4 squares work again. Since all 3 by 3 can fit, then all 4 by 4 could definitely fit. So there's only 4 4 by 4 squares. And then for 5 by 5 squares now, there's only one 5 by 5 square, and that definitely fits. So then there's one of them. So after we add up 1, add 4, add 9 plus 4 plus 1, we have an answer of 19, which is D. This is one way to solve the question. So then we have another way to solve the question. So in this grid, we could count the total number of squares there are, and then subtract off all the squares that do not work. For example, like the squares that do not include the center black square. So there's a total of um 5. So if we plug it into our formula, we could get a total of squares in this grid. So the total number of squares is just 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared. So then this sum is the sum is a sum of 55 right now from this question, from adding all of these up. So then after we figure out the total number of cases, then we count the number of squares that do not meet the requirements of containing the middle black square. So of a 1 by 1 square, then we have a total of 25 minus 1, 24 squares that do not contain the middle black square. So 24 cases that do not work. So then 2 by 2 squares, how many squares do not work? So we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then of 2 by 2 squares, we have 12 squares that do not meet the requirements of including the middle black square. 3 by 3, 4 by 4, and 5 by 5, we do not need to count those remainder cases since we already proved that they include the black square. So this is a sum of 36 now. So out of the 55, so our total starting of 55 minus 36 is equal to 19, which is also another way of getting our answer of D19. Any questions on this problem? Okay, moving on. This is a 2019 AMC 10 problem number 14. For a set of 4 distinct lines in a plane, there are exactly n distinct points that lie on 2 or more of the lines. What are the sum of all possible values of n? I'll give everyone some time on this question, and after I got some answers correct and some correct answers in, then I'll start explaining the question. Okay, so since I only have gotten 2 answers, I'll mention about some of the, I'll give everyone a small hint. So it talks about 4 distinct lines. So we have a maximum number. The maximum number of intersections from 4, we choose, for the 4 distinct lines on a plane, we choose 2 of them. Give me a second. For the 4 distinct lines on a plane, we choose any 2 of them to create a point, and then this is the maximum number of intersections we can have, which is the maximum number of 6 intersections. So then if we have a maximum of 6 intersections, then we can always just always count backwards from 6 to 5 to 4 to 3 to 2 to 1, and we test all those cases to see if that is actually possible to have that many intersections between the 4 lines. And then for the ones that work and the ones that don't work, we then just add the ones that work up together. Just please note, when I say we count backwards from 6 to 5 to 4 to 3 to 2 to 1, I did not say that all of them necessary work. One of them is not gonna, like, one or more of them might not work, so you have to try all of them to see if they work. Okay, just because of time, I'll start talking about this question. We have six. Six we already proved it works because of our handy theorem here. So six definitely works. So then we have to worry about five. Can five intersections work? We could simply just draw a quick figure here between these four lines, and we could see that five intersections. This is six intersections. So then, if we just make the six line parallel, we do indeed have five intersections. So five does work. So then four. Does four intersections work? This also works because we could always just draw the shape like this. Boom. We have if we make these lines parallel, then we could have four intersection points right here. So four does work. So now about three. Does three lines of intersection work? We could test it here. So then we have one line here, another line here, and one line here. And then if we cut this line so perfectly right here through this point and make these two lines parallel, then we do indeed have three lines of intersection. Two intersections. Is that truly possible? The answer is actually no. It is not possible to only have two lines of intersection. If we have two lines that are parallel and we cut a third line through it, where do we cut the fourth line such that it won't intersect those lines anymore? If we cut it parallel, there will be a third intersection here. So then if we cut it like here through this point, it still will meet this line at a point. So two lines does not work. One point intersection, that's just if all four lines meet at one point, and that does work, we say. So then after we add up all three of these numbers, our answer is 19, and it's D. Okay, last question of the night. 2013 AMC 10A problem 25. If all 20 diagonals are drawn in a regular octagon, how many distinct points in the interior of the octagon, not on the boundary, do two or more of the diagonals intersect? I will give everyone maybe 2 minutes to do this because we have to get through it. Okay, just because of time, I will start explaining the question now. It is okay if no one got it because it is a very hard problem as it is the 25th problem on AMC 10. Okay, so if we have 8 points, 8 vertexes, and those are the 8 points, and we have four, we choose four of them out of those 8 to create the number of lines. We get a number of but then again we have to make sure that uh because some of the lines intersect more than one, so we don't know. So we don't know if we overcounted or undercount. We overcounted how much. So since this is 70 right here, and then if we draw out some diagonals, just for a quick example, we notice that a lot of the diagonals intersect at the same place over and over. For example, the middle, if all of the diagonals across the shape, they all intersect at one point. So that one point will be counted over and over again. So then that will be counted more than once, and it will be counted for a total of 7 extra times. So we must deduct 7 from our total of 70. And then after we find that, then we also notice that so if we draw these intersections, they will also meet at the same point again. So of these 3 lines, they will intersect at the same point. So then we have to pick 3, we choose 2 of those lines for intersection. Whoa, give me a second. We choose 3 of those 2 lines, and then we multiply by 8, since there are 8 of those occurrences around the octagon. So then we get another of 24. So then we have to deduct 24 also from the total. And those are all the intersections that we find. And then after we have those intersections, then it's 70 minus 31, which gives us an answer of 49. There is a shortcut to this question. After we notice that um we have 70 intersections that does not include overcounting, we notice that 7 of them are being overcounted in the center of the octagon. So if we minus 7, then it brings us to a total of 63 immediately from here. And then we know there's going to be more occurrences of intersection. And the only answer smaller than 63 from the answer choices is 49. So then we immediately find out the answer is 49 by using the answer choices. But if we go on to Amy and those, they won't have answer choices, so we will have to find out each individual case. But since it's AMC10, we have answer choices, so we always could just single out each of the answers and that. That is the end of today. Does anybody have any final questions before this session is over? Okay, no questions. So, thank you everyone for coming over here to uh, listen to my session. And the session is over. Thank you.